at least if our unperturbed Hamiltonian is just the free particle Hamiltonian, we are able to move with some calculations. Yeah, so this general formulation is not useless because we are able to get to some simpler formulas which in principle we would be able to do. Okay? Okay, I think we still have 1 minute. Let me clean the blackboard and still comment on that, because this is really when we hit the physics. Okay, let me make comments, so I will write it as I had it before. So we derive some function T0 N. So this is just things which is very easy to evaluate in the limit when delta is going to 0, this is going to 1. We don't need to worry about this term. And then we get something here. And the once more I will write it. It is 2 times divided by the volume. Then there is a summation over Kn. I did it for electrons, but I can also do it for bosons, doesn't matter. Calculation will look the same. Important thing is the structure of this denominator. This is the energy of the state Kn minus energy of the state Kn plus Q. Okay, E times H delta for Dani. And then I'm having these probability factors. Before I had it P for the state Kn minus P for the state Kn plus Q. Okay, let's keep it like that. The things is ending. And then we are having this potential VQ to the E QR minus E omega T. Okay, and then I can also have this plus delta, doesn't matter. So this is the perturbation. As a function, and this is at the position R0 and T0. Then we compute this at the position R0, T0. Okay, so this is at the position R0 and T0. So this is given by the perturbation, and we see that the response is going with the same frequency and the same momentum and the perturbation. Then I was telling about this thing. I consider canonical ensemble, and in the canonical ensemble, this P n is a to the minus beta energy divided by the partition function. Okay. If I will use the grand canonical ensemble, and I will go for the fermions, then this P n in the grand canonical ensemble will be Fermi-Dirac distribution at given chemical potential, right? For the given energy En. So it would be 1 over a to the beta, and this is En minus chemical potential plus 1. Only averaging will change, statistical averaging. I am doing everything in canonical because it's simpler. I don't need to keep the chemical potential. But if I will change from rho, which was a to the minus beta H0, H0, and I will go to the grand canonical ensemble, so it would be A to the minus beta 80 minus chemical potential times the number of particles. Then Z will go to grand canonical partition function Z, and these things will give me the Fermi-Dirac distribution. Okay? Try by yourself, just thinking that this is not really the complication, true complication. It's trivial complications. Once we know it, you see the calculation, you can perform calculation in any distribution if you want. Okay. For the bosons, this Pn will be the Bose-Einstein distribution function and energy M, which is A to the A beta An minus mu minus 1. Okay? Okay? So all the things about the ensemble which we are working is just in that case. Okay? Great. We can make immediately the Fourier transform of that. If you would like to make the Fourier transform of this, then we would like to write delta n A at frequency and angular vector q and omega, then we automatically have it. The Fourier transform is very easy. It is just this function which I had times the q. Right? You clearly see that this is the Fourier transform is pretty simple because this exponent which is in the Fourier transform is here, right? So to make the Fourier transform is easy. It is just this function. You see this function is just depending on the omega and the q. So it's just here. Okay? Are you fine? Great. That's the comments I want to make. Last more comment, and this will be in the homework also. I calculated for the free electrons. In the task, in the homework, you will be asked to calculate it for the Bloch electrons in the solids. When the Hamiltonian has some periodic part. So in my case, I just consider p squared divided by 2m and nothing. But now we will consider a periodic potential here. But this is a different periodic potential. This is the periodic potential in the solid. Okay, let's call it W, R. And we know, again, what are the solutions. We know that the solutions in the solid, the eigenstate, are labeled by Cn and K at point x. And this is some periodic part. Times A to the E, K, and X. This is the Bloch theorem. Okay? So the task would be, you need to derive, assuming these wave functions, how this guy will look like. Okay? There will be some modifications appearing here. Okay? We would not be able to get rid of something or something. So actually, you will find out that we would also need to know some integrals over these guys. So we would need to compute the integrals over such things that Un as a function of x, A to the EQX, times M at function of x, that we will need to know such integrals. But if we will know them, let's say by numerics, so write the formula such that you will end up such things, okay? And also be careful, because in the solids, we are having a finite Brillouin zone. So there appears some reciprocal vectors. And the trick which I used before, so you remember before I used the trick that A to the, I don't know, Kn x minus K of Kn minus Km x dx. If you integrate it, I use the fact that this is equal to the volume times delta function Kn Km, right? This was Danny questions or something like that. Or someone asked me, with the sinuses it will be different. But at the end, it will be the same delta function. But since we are working in the solid and we are having a reciprocal vector, then this thing in solid will not work because you need to take arbitrary lattice vector, reciprocal lattice vector. Yes, so there is the difference about that. So I'm just reminding you that when you will be asked to do it, also you can find it in the book. I am following some books. I posted it, so the answer is in some books, so you can find the answer there. Okay, but the thing is that there will appear also something. So the formulation here will be a little bit different. So different system, this polarization function is different. So this is formula just for the free electrons or free bosons or particles which are not in periodic potential. Okay? Good. So this is the comments I want to give. Okie dokie. Yes?
We also need to know the energy dispersion.
Huh?
We also need to know the energy.
Yeah, but you will not calculate the final summation. You just need to come to the formula of that form. That something times something, Bose factor, and something and something. Okay? Some result which we can then use later. Okay? So it will be in the homework sheet, and the answer you will find in the book of the Shoyom. I was, Ming Hao, when he was substituting me, he was showing which books I am following, right? And in one of these books, the answer is given. Also for these and also for the other case, okay? So, just that, okay. So now let me compute the last thing for today. And we are finishing with the linear response. And next week, yeah, the question is whether next week I should give the lecture and then in 2 weeks we will solve the problems? Or you want to solve the problems next week? I don't know what would be the better. But if I will post a homework sheet today or Monday, then you will have more time for preparing. So maybe next week I can give the full lecture, 3 hours. And then we will meet in 2 weeks and just you will solve the problem 3 hours. Okay? So I'm sitting here. I'm enjoying, and who wants to come to the exam, he should always come to the blackboard and do some solutions from time to time, okay? This is for me the entrance ticket to the exam, okay? So who wants to take exam should really solve the problems from time to time. It's also helping you to practice how to give the talk or how to present the things, okay? So it's also some things that you can learn, okay? Good. Then let's go for last thing in this chapter, and this is the fluctuation dissipation theorem. Oh, I'm talking so much, I don't know. I think I should go and retire already. Guys, do you have a feeling that you learned something? Good. Because then I'm talking too much and there is no use of that then. Okay, the problem of the fluctuation dissipation will also be in the homework sheet, and you can find the solution in the script, which I already posted to the Moodle. But I want to show the other solutions, which is not coming from the script. So 2.5. It's a theorem. And I will even show this dissipation part, and also in the homework is just dissipation part. There is also the story about the fluctuation part, but I didn't cover it in the lecture. And so far, I think it's important to know at some point because it says something very important about the nature, but simply then we don't have really enough time to really go to many things. Okay. And I will solve this problem differently as it is asked to be solved in the homework sheet, okay? In the homework sheet you should follow different path, but you will see the result is the same. So assume now that my perturbation is again some operator O, okay? And there is some constant, and there is a cosinus omega t. So I am having a real perturbation which is going with some frequency omega t, and there is something such that has a dimension of the energy. I have some operator O, so I need to multiply it properly with something such that it has a dimension of the energy. Okay. So my perturbation, and I will just apply just standard quantum mechanics. Okay, you don't need to know linear response, nothing else. So just this I understand from the eyes of the standard quantum mechanics. And what I'm seeing here, if I'm looking with the eyes of the quantum mechanics, then I see I have a time-dependent potential. Right, and if you have a time-dependent potential, that if you remember your classes from the quantum mechanics, then you can apply the time-dependent perturbation theory, and you can derive the Fermi golden rule. And this Fermi golden rule is telling you something like that, that the probability, this is called the probability per unit of time that the system goes from initial state E to final state F, right? Do you remember this? Fermi golden rule, did you have it, right? So this probability per unit of time, sometimes it's written also like that, that you really say that it's some number divided by time. So this is the probability per unit of time. And according to Fermi golden rule, this is 2p divided by h. And then you need to take this Hamiltonian and compute the expectation value. So you are having final state, operator O, initial state. You need to repeat this, right? And then you will get a delta function. And actually you will get two delta functions. So this is the delta function EF minus EE H omega plus delta function EF minus EE minus H omega. Oh, sorry, this is EE minus EF. So please consult your quantum mechanics on Fermi golden rule. And there are really two delta functions. Normally this one is not written, but this one should be there if you look for the derivation, and this thing is responsible for the spontaneous emissions. You have absorption and emission, right? What you can have is, just to give it you, so what this formula is telling me, that if I have the energy levels in atoms or in somewhere, so if this is the initial state, right, then the initial state can be excited to the final state which has a different energy. So this is initial state, this is the final state, this is the energy of the initial state, this is the energy of the final state. And this delta function is telling me like that, that energy of the final state is, sorry, I wrote it minus, everywhere is a minus. So this is final, minus, initial, like that. So this tells me that system is absorbing the photon and is excited, right? So this is the first delta function. But we know how the lasers are operating, and we know that in the lasers you can have opposite situations, that you are having a state here, this is the initial state, and if there is a coming a light, what can happen is that it stimulates electron going down to the lower energy state and emit another photon. And then you are creating a coherent lasing. This is the principle of the lasing, that you are having a stimulated emission. This is this thing in the delta function, okay? Good, so this is the Fermi golden rule. So now we will use the Fermi golden rule and we will compute how much energy the system is absorbing and how much energy the system is losing by that, okay? So I will use these things, okay? Can I go on? Great, so we know the Fermi golden rule. So then we can compute the probability per unit of time. So let's compute the following things. Let's compute the probability per unit of time that the system absorbs energy h bar omega. Okay, so probability per unit of time that the system absorbs energy is nothing else as the power. So I'm computing the power of the gain, which is the energy divided by time. Yeah, this is the power. It's a time. It's a derivative of the energy with respect to time is a power, right? How the energy per unit of time. So this we can compute, and now we can compute what is the gain of the energy by the system by exactly the process which I described you. I have a system with energy levels. They are occupied at the beginning. Some of them are empty. Yeah, this is empty. For example, this is occupied and there is empty. Now comes the light, and what we are getting is that some states are getting excited and system is gaining the energy. And I'm going to compute how much energy per unit of time is system gaining from the perturbation, okay? And it's very easy, so we can start to compute it. So it will be sum over the initial and final states. And I will explain everything. So we are adding the energy of the system, so this is h bar omega I am computing. And now I need to compute how much, and now I need to do some statistics. Okay, so I am assuming that the system is in the thermal equilibrium at the beginning, so the probability to find the state E is Pi. It's a probability that the state E is occupied in the equilibrium, right? If the state E is getting the energy, it is excited to state F, and this state should be empty. Right? So in the case of the fermions, I need to find the probability that this final state is empty. So this is the probability that the initial state is occupied. This is the probability that the final state is empty. Right? Great. And then the 1 over tau E, I'm just using the Fermi-Golden rule, and this is 2p divided by h bar f omega squared. And then I'm having this probability of phi f, so this is the wave function operator O, the initial, and then I am having a delta function, but I have only this delta function because system is now absorbing the energy, minus AE minus h bar omega. So the final energy should be larger than the initial energy because only in that case I am able to absorb something, right? That I am doing excitation, right? Is that clear? Is that fine? This is only in the case of electrons, because the Pauli principle. For the bosons, I would not have anything here, because bosons can occupy the same energy level, okay? But I'm doing it, you will see that final formula does not depend whether we are discussing bosons or electrons, but I'm just doing this calculation for electrons particularly, okay? Great. Now let's compute the probability of losing energy. That during the process that the system is losing energy. Okay, so again it would be the energy h bar omega over some time. And again I need to do the summation over initial states and the final states. The system is losing energy omega because I'm just assuming that I'm pumping the energy with the frequency omega. So only energy which I have is h bar omega. And again, this is the probability that the system is occupied, probability that the final state is empty. This is 2p divided by h. This is the same square. This is, everything is the same. Only we are taking now the different delta function. Now we are taking the delta function E is larger than the final state minus h bar omega. So I'm taking the second delta function here, right? This corresponds to the stimulated emission. System has some energy, something perturbed him. It perturbed him and he said, oh, I can release my energy and go down. Okay? So this is the thing. Do you see it? All fine? Do you understand the physics what I'm doing? Great. So now I will just do things that I will rename the indices here. So this is the sum over all states. So let me rename those states. So I'm just renaming the indices. And if I'm renaming the indices, this will be F, this will be E. Okay? This will be E, this will be F. This will be F, this will be E. I can do it for free because I'm teacher. No, because things does not depend how I name the indices, right? Is that also clear, right? So now we can compute what is the change of the energy of the system with respect to time t. This is the amount which I am gaining minus the amount which I am losing, right? This is the at the end this is my netto. You have income, you need to pay your taxes. So your income is brutto, your taxes are loose, so your netto income is the difference between brutto and taxes, right? This is exactly the same thing, okay? So if I'm doing it, so I need to subtract those two things, so let me do it, and I'm writing the result. And you clearly see that we just need to pay attention with this term. Okay, delta function is already in the fine. We just need to pay attention with this term because this term is written like that. It is Fe, operator O, operator F, and then I have operator F, O. This is absolute value. So then I can write it like this. Okay. Complex conjugated, and it will be like that. Okay, this element is this. You see it? This element is this. Okay? PFE. Okay, complex conjugated, and here I have it opposite. Okie dokie, and what I did here? No, I'm doing something wrong, right? This is, since it's the absolute value, I don't need to care, right? Okay, let me write. Let me write what I want. So I write the result, and let me see whether we see it. So it is 2p divided by h. Then we are having this f omega square. Okay. Then I'm having h bar omega. And then I'm just having sum over e, sum over f. And then I have this pe minus pf. And I just wrote his, that this is P final, operator O, P initial, and square. Okay, but I somehow, but please, maybe, okay, then I next time need to clarify. Somehow in my notes I just said that, okay, this is the same as this. Is it clear that this thing in the absolute value square is the same as this thing? Yeah, if it's Hermitian, then it's true, right? Okay, then let's assume that it's Hermitian. But it should be Hermitian, otherwise we are not having a perturbation which is Hermitian, right? So it's non-physical in some sense. So let's assume it's Hermitian, okay? Good. But then we are getting this thing and delta function. Okay? Great. But if you look for the formula which we derived before, and I'm just writing here the result. So you remember we started with the imaginary time of the susceptibility. So imaginary time, or imaginary part of the susceptibility for the operator O and O is basically exactly this expression. Some minus P is also there, right? So the imaginary time, this is exactly minus P and this summation. But before I have N and M, just remember that the difference is that now I have the initial and final, but that was the formula which we had for the imaginary part of this, that it was N, O, M, M, O, N, and the delta function H bar omega plus N minus N. Okay. This was the formula for the imaginary part of the susceptibility, which I defined general. So basically this is here, a part of this minus EP, right? But if I will install it back, so let me continue here. What we are getting is that the dE with respect to dt is equal to minus 2f omega squared, and this is omega times the imaginary part of the susceptibility of omega. H bar cancels. F omega squared survive, minus 1 over P, so this is minus 2, yeah, because this P is missing, so I'm getting this result. Okay? And I show you that this thing is always larger than 0. Or we saw from the form of the expression that it's always larger than 0. Okay? So this is the dissipation of the energy. So we are seeing that perturbation of that form, at least, if the perturbation is of that form, that it is like F omega, some Hermitian operator times cosine omega t, then we see that what happens is that the system is basically absorbing the energy. The total energy of the system in time is growing. That's what we show. Yeah. So this is the total energy as a function of time is growing. So we see the system is absorbing the energy. So perturbation is losing energy. If you want to keep the perturbation, you need to fill it with a battery, or you need to drive the system to be in perturbative regime. Did you get it? Okay. Danny. Yes. Yes. So losing energy is emission. Yes. Oh, it was just the index, right? All the care about the things was in these probability factors. And what do you mean? Yeah, but also these things switch the roles, right? The main point was that the delta function was different. Yeah, by this switching, I bring the delta function to be the same. And then I can make the one delta function in these expressions. And even this is exactly good point what you are asking, because the probability to occupy the, so you see that this thing should be positive. If the final result should be positive, okay, if you just look for these things, just out of these things, this is positive, this is positive, absolute value, delta function is even function, so it's a positive, right? And I am claiming that the final result is a positive, which tells me that probability of the initial state minus probability of the final state should be also positive, which is normally the case in the equilibrium, right? Because in the equilibrium, you are having the states, so the probability to find the states with lower energy is higher than to find the states with higher energy. And so it's also positive. Chepin, are you with me? Sure? Follow? Very good. Okay. Good. So this is about the linear response. More problems are in the homework sheet. I really strongly enforce you to do the homework sheets, and we present the, because we still will discuss some physics then on the blackboard, so it's up to you. If you will not do it, we will not have it, but you are just scooping yourself, you know, so it's important about it. So I didn't cover, there are still many things, these fluctuation parts are part of the susceptibilities, there are also some correlations functions which are important. But I simply don't have time to cover everything of that, okay? Because we are just limited to 3 hours per week. Normally such lectures should be given like 4 hours per week in some universities. Then I was before, it was the standard format. So we are basically losing 1 hour per week because that's the habit here. So I'm just telling that I need to cut some things, okay? Good. We still have maybe 10 minutes, right? Or 7? 15? Ah, okay, then great. We only have 15 minutes? Didn't I scoop you 20 minutes break? Because there, I finished something and I should write, we started at 9 and we should start at 9:10. Shouldn't I? So what we can do is we can stop or we can continue? Continue. Great, then we can continue, and we are continuing. Or do you have a question so far? That we can use maybe this time for questions and I start next time? New chapter? Or I can start the new chapter. Do you have questions? Okay. Then not, then I'm starting the chapter. You can write, or you can go and write it on the blackboard if you want. Yes, this is dissipation, that system is taking the energy. So energy is dissipated in the system. So yes. And in the homework sheet there will be another approach. Oh, in the script there is also explanation of that. Just look the script. I posted it yesterday in the Moodle. There is a chapter in the script, fluctuation, dissipation, and they are doing it a little bit differently. They're using equation of motion for the density of states, and they came to the same conclusion. Okay? So this is only the difference. But I did it somehow connected with the physics. Fermi golden rule, absorption, emission, and we see it. Other way would be formal. We are having a perturbation, fine, it's written in the script. We take the observable, this is the energy. Energy is observable, so we can compute correlation function between, or the susceptibility between energy and the energy, which is perturbation. And we will get the same result. Okay? So just really look for the script. Okay, so I'm going now into the chapter number 3. And this is the second quantization. So we go to the new chapter. Second quantization. So how much time do I have? Just please tell me. I have a feeling that I don't have time, right? Three minutes, right? No. Actually, I want to terminate because it will be better that I will start next time with that. So I think it's to start new chapter and then leave it 1 week is not a good idea. But I have just really 2 minutes now, right? So I think we will start next week with that. So let's do it like that. Next week I will do again 3 hours. I will make this second quantization, which is again mainly talking. So did you hear about the second quantization before? So I don't need to describe it so much, or I don't know, I just need to know like how deep I should go. Whether I should go deeper or deeper is fine. Okay, deeper is fine. This is okay. Then we will start with the second quantization, and then next week after, I think it's 28. You will just solve the problems on the blackboard. I will be sitting, I will be popcorn, Coca-Cola, and you are solving the problems. Okay? You'll be prepared for that. Everyone should be able to solve at least 1, 2, 3 problems. We will come and we show the solution. Main step. This is the thing you need to make this. Not all the details of every calculation. Just mainly describe how to get to the result. Start there, we use this, we get this integral. This integral can be calculated like that. We make the substitution, then part test, this is the outcome. You know, like making it like that style, okay? For pedestrian, not for you. Every step, because we will be able to not do that. Okay? As much we solve, the better. Okay? That's it. Thank you.